experimental and the theoretical probabilities together. So the first thing I'm going to do is I'm going to identify what the theoretical probability is. Remember, theoretical probability is based off of the item itself and not the action that is occurring. It's based off of the item. So the item happens to be a coin. A coin, that's where we are going to identify our theoretical probability. For a coin, what is the probability that it's going to land on heads? 1/2, right? Heads occurs one time on the coin out of 2 possible outcomes. Remember, you want to make sure you identify it in both fraction, decimal format, percentage format. So we've got 1/2, we've got 0.5, we've got 50%. You need to know all 3 formats because you don't know which format they're going to use. Okay, that's our theoretical probability. The experimental probability is based off of the experiment that happened, meaning that there had to be action. So the action is right here. It was tossed. Tossed is an action. It's a verb, right? So our experimental probability that the coin is going to land on heads is 28 times out of 50 trials. 28 times that it landed on heads out of 50 trials. Now, as always, you want to simplify it. Both are divisible by 2. That's going to simplify to 14 over 25. That's as simplified as it will get. As a decimal, that's going to be 0.56. As a percentage, that's 56%. Okay, so we have our theoretical probability, we have our experimental probability. Now we need to make a comparison. So based off of what we're seeing, we know the experimental probability currently has a larger probability of landing on heads than the theoretical. Again, why is that? What is the cause for that discrepancy to be 6% off from the theoretical? What needs to happen? Maya? They didn't do enough trials. Maybe if they did 100 trials, maybe they would have been closer to that 50%. 1,000 trials would get even closer to that 50%. 1,000,000 trials would be very close to that 50%. The more trials that they perform, the smaller the room for error is, the less discrepancies that we'll see. But let's go ahead and write down that the experimental probability of 56% is greater than the theoretical probability, which was 50%. But again, the goal in mind is to get to the theoretical. That's the goal, right? Theoretical is kind of like it's the correct answer. Experimental is the process of getting to the correct answer. Okay? All right, problem number 2. You have 5 green marbles, 2 purple marbles, and 3 blue marbles. You're going to pull a marble from the bag, record it, and place it back in the bag. You need to compare the experimental probabilities and the theoretical probabilities. So here, these are the results that you recorded. That when you pulled the marble out of the bag, you got 15 times it was a blue marble, 25 times it was a green marble, 5 times gave you a purple marble. This right here being results of your experiment, this is going to represent your experimental probability. I'm going to put EXP right here. Our theoretical probability is based off of what do we have? We have 5 green marbles, 2 purple marbles, and 3 blue marbles. This is going to be how we compare or how we create our theoretical. Okay, before we start pulling marbles out of the bag, we have to know which marbles do we have and how many of each color. So we'll create our theoretical probability for purple. Theoretical probability for purple. In the bag, how many purple marbles do we have? 2. We have 2 purple marbles inside of the bag. Out of how many total marbles are in the bag? 10, right? 5 plus 2 plus 3, that comes out to 10. So our theoretical probability, if we simplify it, is 1/5. 1/5 as a decimal is 0.2. 0.2 as a percentage is 20%. Okay, now we can go on to the experimental probability, which was us physically pulling these marbles out of the bag and recording those results. How many times did we actually pull out a marble that was purple? 5 times. Out of how many total trials? 45. So 5 over 45 can simplify to 1 over 9. 1 over 9 is going to come out to 0.1 repeated, or we'll just go ahead and put a 0.11, and that's approximately 11%. Approximately. Okay, so instead of putting equals, we're just going to put the little wavy sign. That's an approximation. Okay, so now we're going to make our comparison. In this case, our theoretical probability, which was 20%, is greater than the experimental probability. Did she startle you? She'll do that every once in a while. When she gets excited, she'll run around the cage real fast. Okay, any questions? Now, again, I put a big reminder down here that in order for you to have a closer representation, in order for your experimental probability to be closer to your theoretical, you have to have more trials. That's a big, big deal. I'm going to go ahead and highlight this thing, this whole entire statement. Okay, to get experimental probability as close as possible to your theoretical probability, meaning it's almost equal, you must perform a large number of trials. And be careful, because I've seen people before mess up and they say, oh, it's a large number of outcomes. Are outcomes the same thing as trials? No. Outcomes and trials are different. So you need to make sure that you understand. Trials means how many times you perform your experiment. How many times did you flip the coin? How many times did you roll the die? All right. Using probability to make predictions. That's what our lesson's on today, is making predictions based off of probability that has been provided to us. We're also going to learn about a little concept called fundamental counting principle as well. But when you are making predictions using your probability, you're going to set a problem up using what's called a proportion. Raise your hand if you remember what a proportion is. Okay, Dakota, can you share with us what a proportion is? You don't have to use this problem. Just give me an example of what a proportion would be, or what it might look like. Okay, unit rate. Unit rate is used with proportion sometimes. A comparison, okay, it's a comparison. What format do we typically see the problem written with? With fractions, okay? We typically see them written with fractions, which makes sense if we're using probabilities. Probabilities, main format of writing, is in fraction form. So we're using a probability to predict a certain amount out of a certain total, or to predict a total out of a certain given amount, okay? So proportions takes two ratios are fractions, and sets them equal to each other. If you have something that is unknown, you then can perform the cross product, meaning you can multiply diagonals and solve with a basic one-step equation. Okay, so let's take a look at this situation. Yesterday, 50 customers bought muffins, and 12 of those muffins were blueberry. So on Friday, I expect 75 customers to be coming in. So how many blueberry muffins should I prepare? Guys, this is a very common concept. When you are a store owner or a restaurant owner, you have to look at what are you selling? How many people came through your storefront that day? How much of this specific item did you sell, so that you can go ahead and prepare to sell more of that stuff based off of how many customers you expect through a trend. So if I know that, Wednesdays are my slow days, Wednesday's my slow day, so I'm going to only take out, 20 pounds of fish because that's my slow day. Not a lot of people come through my store. Not a lot of them are going to order the fish item. So I'm only going to take out 20 pounds. That's probably going to go ahead and suffice. But based off of using that 20 pounds on Wednesday, if I know that on Saturday's my busiest night, and I usually see like 5 or 6 times the amount of customers, then I'm going to need to take out 5 or 6 times the amount of fish just to prepare, because you don't want to be the person who runs out of an item. Okay? Now, here, 12 muffins out of 50 customers. I want to know how many muffins out of 75. So what you do to set this up is you set it up as a probability prediction. What I mean by probability prediction is you identify what the probability is in the problem. So in the problem, my probability is based off of here, what I know, that there were 12 muffins out of 50 customers. I had 12 muffins out of 50 customers. And then I'm going to go ahead and I'm going to set this equal to what we call the prediction. So I know my probability that 12 out of 50 customers, that's my experimental probability. 12 customers got blueberry out of 50 customers that came in. Now we're going to make a prediction. I want to know out of 75, how many blueberries are there going to be? Okay. So I need to know how many blueberry muffins out of 75 people. Guys, it's always a good idea to label sometimes, because that's one of the things people make a mistake on, is reversing or flipping the way that they would do it. So if I know that this is representing the blueberries and this is representing the people, then I need to make sure that on my prediction, I've got blueberries on top and I've got people on the bottom. It needs to be a good mirror, a good mirrored representation. Once I've got my proportion set up, I then can use my cross product to go ahead and solve. So for cross product, I'm going to multiply my diagonal values together. So I'm going to multiply 50 times x, and that's going to give me 50x. And then I'm going to multiply 12 times 75. Do that real quick. And that's going to give me 900. We're going to do 50 times x, and we're going to do 12 times 75. Okay, this creates a one-step equation. To solve my one-step equation, I just divide both sides by 50. Okay, so 900 divided by 50 is going to come out to 18. So I'm going to go ahead and take out 18 blueberry muffins. $18 blueberry muffins is what I'm going to expect to go ahead and sell. So I'm going to make sure I make 18 blueberry muffins. Okay, let's go ahead and as soon as you finish copying this down, let's go to the next page. So for problem number 2, a bag of fun-sized Skittles has 2 purple, 3 orange, 6 yellow, 1 red, and 1 green. If a king-size bag of Skittles has 150 Skittles in it, then how many purple would you expect to see in the bag? Okay, so again, what we need to do is we're going to set up our probability first. We're going to set up our probability proportion first, or probability ratio first. So the probability of purple, what's the probability that purple is going to happen for the fun-sized bag? How many purple do we have? 2. How many total Skittles are in the fun-sized bag? Okay. Right? 2 plus 3 plus 6 plus 1 plus 1. That gives us 13. So we have 2 out of 13. Okay, now we need to set this equal to our prediction that we want to make. We want to figure out how many purple out of 150 Skittles inside of the king-size bag. Okay, so we made our probability based off of this information here. We're making a prediction based off of the fact that our king-size bag is going to have 150 in it. Go ahead and scroll this up now a little more. And we're going to set these equal to each other so that we can then solve. We're going to do our cross product. We're going to multiply 13 times the x. I'm going to go ahead and just write that over here. We're going to get 13x. We're going to multiply 2 times 150. 2 times 150 is going to give us 300. We're then going to go ahead and divide. So we'll divide both sides by 13, and we're going to get an approximation. We want to estimate it. So if you do 300 divided by 13, it's going to come out to 23.07. So what would we round that to as a Skittle, as a whole Skittle? About 23, right? 23.0 is about 23. 23.07, that would be 23. Okay, so it's approximately 23 purple Skittles. And again, these are predictions. Are predictions ever exact? No. Right? Maybe I might have 27. Maybe that king-size bag decided that it really loved purple Skittles that day and has a whole ton. But we're trying to take information that we know and predict based off of that. I want you guys to go ahead and try numbers 3, 4, and 5 on your own. Problems 3, 4, and 5 on your own. All right, let's go ahead and go over this. For problem number 3, the probability of pulling a red marble is 2 ninths. If there are 7 reds, then how many total marbles are there? Approximately how many total marbles would there be? All right, so our probability right here is 2 out of 9. So we're going to set that equal to the prediction. Now here, this is a little bit different. They're saying that there are 7 reds, so how many total marbles are there? So remember, for probability, this represents the red out of the total number of outcomes, right? How many red out of a total number of outcomes? So for here, they're telling us the number of red. So 7 is going to go on top. 7 red out of how many total marbles? Be mindful of that. That's where the big mistake comes from. You got to read carefully to identify what actually is going on top, which is actually going to go on the bottom. Okay, we're going to go ahead and do our cross product. We're going to multiply 2 times x. That's going to give us 2x. We're going to multiply 9 times 7, and 9 times 7 is 63. And then we're going to go ahead and divide both sides by 2. And we can assume that there's approximately 32, right? Comes up to 31.5, so that's approximately 32 marbles inside of the bag. Okay, for problem number 4, table shows the necklaces sold in 3 sizes in 2 different metals by a jeweler in July. So this is representing all that happened in July. If he plans on selling 100 necklaces in August, how many of them would be 20 inches gold? How many of them would be a 20-inch gold? So that's focusing on this piece right here. 20 inches gold. Okay, so right now we need to go ahead and set up our probability. Our probability is 12 of the necklaces are 20 inches in gold. out of how many total necklaces did he sell in July? 75, right? If you add all of those together, it's a total of 75 necklaces that he sold. Now we need to make a prediction. He wants to know how many of them are going to be 20 inches in gold out of 100 total necklaces that he's going to sell. So we're going to multiply the 75 times x to get 75x. We're then going to multiply the 12 times 100. That's going to give us 1200. And then we'll divide both sides by 75. And we can expect about 16 necklaces. That'll be the 20 inches gold. Okay, the last question here. If you roll a die 21 times, we want to predict how many times you might land on a number that is greater than or equal to 3. So greater than or equal to 3. What's the probability of getting greater than or equal to 3 on a number cube or on a die? 4 out of 6, right? That would be a 3, a 4, a 5, and a 6. There's 4 different outcomes you could land on out of 6 total outcomes on the die. We want to set this equal to the prediction. So we want to roll the die 21 times. We want to know how often might we land on a 3 or greater. So we'll do our cross product. 6 times x is 6x. We'll do 4 times 21. 4 times 21 is 84. And then we'll divide both sides by 6, and we're going to get about 14 times. X will equal 14. All right, any questions about using probability to make a prediction? Simple stuff. It's just using the concept that you guys have used often with proportions, ratios and proportions unit. All right, let's look at the last page. The last page is super, super easy. Fundamental counting principle. It's probably the easiest concept out of all for our probability unit. So the fundamental counting principle states that if there are p ways to do one thing, and then q ways to do another thing, then there are p times q ways to do both things simultaneously. Okay, and what I mean by that is if you have an activity, activity A, so you're going to take the total number of outcomes, total possible outcomes of activity A, and you're then going to multiply it by the total possible outcomes of activity B. So think back. Yesterday, we rolled 2 dice. And we listed out all the different possible outcomes that we could create with those 2 dice, right? We were like, oh, it could be a 1-1, a 1-2, a 1-3, a 1-4, a 1-5, a 1-6. It could be a 2-1, 2-2, 2-3, 2-4, 2-5, 2-6. And we listed all of it out. How many total outcomes did we come up with? 36. We came up with 36 total outcomes. That should make sense now because how many outcomes are on one die? 6 outcomes. So there's 6 outcomes for activity A. How many outcomes on the second die? 6. 6 outcomes for activity B. And what is 6 times 6? 36. What do you think is the most commonly chosen wrong answer when I say you have 2 dice? How many total outcomes? 12. That is the most common incorrect answer because they say, oh, well, each die has 6 outcomes and there's 2 dice, so I'm just going to multiply it by 2. But that's not what you do. You take the number of outcomes for the first one and the number of outcomes for the second one, and you multiply the outcomes together, not outcomes times the number of activities, okay? So be mindful of those common mistakes that people make. Let's take a look. We have 8 shirts, 8 shirts, 6 jeans, 3 pairs of shoes. I want to know how many different outfits that I can create with 8 shirts, 6 jeans, and 3 pairs of shoes. So I have 3 different activities here. I have activities of shirts. So I'm going to take the number of shirts that I have, which is 8, and I'm going to multiply it by my second activity. My second activity is choosing some pants to wear, some jeans. So I have a total number of 6 jeans. And then I actually have a third activity. My third activity happens to be shoes. And I have 3 pairs of shoes that I can wear. So all I have to do is multiply 8 times 6 times 3. What do we get when we multiply 8 times 6 times 3? Use your calculator. 144. Very good. So you have 144 total outfits. 144 total outfits that you can go ahead and create. Now, this also works with finding probability. The fundamental counting principle, you're multiplying to find the total number of outcomes, but you can do that with what's called compound probability. You can find the probability of each specific event and multiply those together, and that will be the probability that all 3 events will happen simultaneously. So let's try that out. Out of the 8 shirts that we have, 2 of them are white, 3 are black, and 3 are red. Out of the 6 pairs of jeans that we have, 4 are blue and 2 are black. Out of the 3 pairs of shoes that we have, 1 pair is flip-flops, another is sneakers, and the last pair is dress shoes. I want the probability of choosing a white shirt, black jeans, and dress shoes. White shirt, black jeans, dress shoes. So let's split this up. Let's first find the probability of a white shirt. Probability of a white shirt. So that's based off of this information that has been given in the first line. That out of the 8 shirts that we have, we've got 2 that are white. So that means that probability is 2 over 8. Not going to worry about simplifying yet. Not going to worry about simplifying yet. Okay, we're going to move on to the next one. The next one is black jeans. So the probability that I'm going to choose black jeans, that's based off of this line. Out of the 6 pairs of jeans, we've got 2 that are black. So we have 2 pairs of black jeans out of the 6 pairs of jeans that we have. And then our last line, out of the 3 pairs of shoes that we've got, 1 pair of those are dress shoes. So the probability of dress shoes is 1 out of 3. And all we have to do is multiply. So if we type in 2 8s times 2 6 times 1/3, that's going to come out to 1 over 36. Okay? All right, go ahead and do problem 3, 4, and 5 on your own. Problem 3 should be easy because you already know it. For problem number 3, what is the total number of possible outcomes with rolling 2 dice? 36, right? We have 6 possible outcomes for the first die. Multiply that by 6 possible outcomes for the second die. That's going to come out to a total possible outcomes of 36. What about if we have 3 different coins? We have a dime, a penny, and a quarter. How many total outcomes are that, Divvy? 8, right? We have 8 total outcomes. We've got 2 outcomes for a dime. We have 2 outcomes for a penny, and we have 2 outcomes that the quarter can land on. And 2 times 2 times 2 comes out to 8. Okay, and what are the total number of possible outcomes for spinning a 5-section spinner and flipping a coin? 10, right? We have a 5-section spinner, and a coin's got 2 options. And if we multiply 5 times 2, that's going to come out to 10. Go ahead and get into your computers. We're going to play a game kit.